Hello students of science. In this video we're going to talk about the molecular basis behind liquids and solids. So in your notes I want you to make a mini little table like this: gas, liquid, and solid. So we're going to look at some of the similarities and some of the differences between them. Here you can see we have gas molecules very far apart, not very dense at all. Liquid, we're going to see that we definitely have particles much more closely packed, and solid the most closely packed of all of them. Now, one thing that gases and liquids have in common is that they're fluid. They don't have any shape. They will take the shape of whatever container it happens to be in. You would call this fluidity. Here we have like a fluorescent dye actually coming out of a beaker, and you can see a liquid here, like a gas, will take on the shape of whatever it's in. Solid has a definite shape. You can maybe change that shape, but it will maintain that shape regardless of what happens. Unlike the other two, gases do not have a definite volume. Basically, you release gases in an enclosed area, they will take on the entire volume of that area. Liquids will not do that. They will take on the shape, but they have a set volume. So, liquids and solids do have that in common. A definite volume. They're not just going to take on whatever volume they're in. Gases, as you can see in this image here, not very dense. Very large amount of space between particles. That's what makes them able to be compressed. Liquids, very dense. Solids, extremely dense. As I mentioned before, because of this large space between all the particles, gases are very compressible, whereas liquids and solids, for all intents and purposes, cannot change their volume. You have to do extreme things to make them change their volume, so for now we're just going to call them incompressible. And finally, diffusion. Gases and liquids both will have diffusion. If you have someone walked in the room wearing stinky cologne, that is going to diffuse through the gases. If you put food coloring in water, that's going to diffuse through there. Solids, you're going to put two solids together, they're not really going to diffuse at all. So, things that gases and liquids have in common: fluidity and diffusion. Things that liquids and solids have in common: they have a definite volume, they're very dense, and they're incompressible. You cannot change that volume. All right, so looking at these four ones here, let's try to figure out what they are. I'd start right here. This one, the particles are moving the fastest and they are the least dense. That one's going to be a gas. This one here, I can see the particles are much denser, so we know it's not a gas. However, they are freely moving past each other. In that case, that means it's a liquid. So what we're left here is these two here. This one's going to be a solid. You can see the particles have a definite shape, a definite volume. They are moving, which means this one down here, where they still have that definite shape and definite volume, it's just at a higher temperature. That is a hot solid, more kinetic energy in each particle, but not enough to actually turn it into liquid. One characteristic of liquids: they have surface tension and capillary action. This is only you're going to see in liquids. Surface tension is a force that's going to pull the liquid surface area closer together. So this intermolecular attraction, water is a great example. Those particles are all being attracted to each other. What this means is that you almost have this little surface at the top where the water wants to stick to itself more than it wants to stick to anything else. Then you get these creatures like these water striders that actually exploit this. The water wants to stick to itself, not anything else. Well, that's what the water striders want as well. So they almost have this trampoline, this cushion that they can walk around on. Here you can see dropping a water droplet on water. There is that surface tension. Even between two drops of water, it does not necessarily want to merge right away, so you get a little bit of surface tension. Capillary action is the attraction between that surface of the liquid and the surface of a solid. So you're going to see we have this intermolecular attraction. It's also, when you get it near the edges of like a straw or something like that, it's going to stick to the edges and climb up a little bit there. So that capillary action is as a result of the water sticking to itself and sticking to the edges of the cup. This is going to pull up liquid on a surface against gravity. If you ever put like a paper towel in water, it's going to do the same thing there. Water sticks to itself, but it's going to stick to other things as well. All right, let's talk about solids. Particles of a solid are more closely packed than either liquids or gases, so they pretty much always are the densest. Water is the rare exception to this solids are denser than liquids rule. Water is one of those rare things where the solid form, ice, actually floats. If it was like most other compounds pretty much in the universe, ice would sink. We're very fortunate of that because it probably enables life to happen. But solids, usually denser, ice being the rare exception. Solids have a definite shape. Even if you take away a container, they are going to maintain that shape, and a definite volume. They're not going to fill up a container that they're in. High density, as I mentioned, and incompressible. There's not really just enough space in here to even squish them down anymore. Even if you're squishing something like wood and like a vise or something like that, you're really only squishing the air inside it, not the particles itself. Solids are grouped into two main things. We've got amorphous and crystalline. Let's start with crystalline. In a crystal, particles are arranged in an orderly geometric repeating pattern. This is actually a crystal of sodium chloride. The larger ones there are going to be the chlorine, the smaller ones are going to be the sodium, and you can see there's a very regular pattern. This is why crystals of salt or salt granules have a very definite shape, and it's a very geometric shape as well. The smallest unit of a crystal in a repeating 3D structure is called a unit cell. So a unit cell here would consist of the sodium and chlorine, if you almost imagine those as a small cube there. Here's a larger crystal, and the unit cell is the smallest individual particle of it. Examples of crystalline solids: snowflakes, diamond, table salt. If you ever think of any crystalline materials, they take on that geometric shape because at the molecular level, they have pure geometric shape. This is actually diamond, and you can see a very clear, very consistent pattern through there. That is a crystalline structure. Now, the other kind of solids are amorphous. Morph means shape. When you put a in front of it, it means not or without. So amorphous literally means without shape. In this case, particles are kind of arranged randomly, so you get this bit of a jumble around there. Examples of amorphous solids would be glass and plastics. Here, crystalline, very ordered, very regular. Amorphous, just kind of all over the place doing its thing.